Namaste. Welcome back to the course on physics of nanomaterials. Let us continue our discussion on the conduction electrons and electron tunneling phenomena, which are seen as the driving force for the observed modulations in the properties of nanomaterials. In today's lecture, that is lecture number 15, we will talk to you about the Fermi gas and the concept of density of states once again. I have talked to you about density of states in the previous lectures. So, we will look into it slightly more in detail, and then we will see what happens when these parameters change. So, in today's lecture, we will talk to you about the concept of Fermi gas and electron delocalization. What do we mean by that? Now, if you go from 1D to 2D to 0D materials, that is nanomaterials, the density of states are expected to vary. And how do they actually vary? This is what we are going to discuss in today's class. And then we will also talk to you about the concepts of Coulomb interaction and exciton formation. So, in today's lecture, we will talk to you about the concept of Fermi gas and electron delocalizations. How does the density of states varies in different nanoparticles? That means, when we go from bulk to quantum well structures or quantum wire type structures or structures where you see all the 3 dimensions in the range of 1 to 100 nanometers, that is quantum dots, then how does the density of states change? And if time permits, we will also talk to you about the concept of Coulomb interaction and exciton formation. If not, then we will talk about these concepts in the next lecture. So, if we see the classical description of the conduction in metals, we have seen that there is a concept which was discussed, that is free electron model or nearly free electron model. And then we had talked about the formation of bands, that is energy bands, and what do we understand when there is a free electron? Then it is actually seeing 2 types of confinements. One is throughout the length of the material and the second is around the atoms. So, you have 2 types of systems which are being simulated inside a given particle. So, in metals what happens? You know that the valence electrons dissociate from their parent atoms. So, if you have the conduction band and valence band, then you find that the electrons are actually dissociated from their parent atoms and they are free to move in the continuum of the conduction band. Now, they are delocalized, that means they can move freely throughout the metallic lattice, but when they are dissociated from their parent atom, what happens? The parent atom actually simulate a background of positive metal ions. For example, if it is coming out from sodium or aluminum or silver or gold, then you have Na plus, Al plus, Ag plus, Au plus. So, these are the background of positive metal ions. These delocalized electrons are treated as Fermi gas. This is a gas comprising of a collection of non-interacting fermions, in this case electrons, which follow the Fermi-Dirac statistics. So, you consider these electrons as the non-interacting fermions. Now, these electrons can move through the metal with minimal hindrance. Why? Because they are free and they are non-interacting, so they see minimal scattering. And before any collision takes place, that means a scattering takes place, they traverse a mean path of L before seeing a scattering phenomena taking place. Now, if you associate the energy, that is because they are moving, so you associate the kinetic energy. So, you have half mv square, where m is the mass of the electron, v is the speed of the electron. You can write this in terms of momentum, that becomes p square by 2m. So, p is the linear momentum of the electron. Now, in classical model, please also remember, we also know the concept of Ohm's law, where V is equal to IR, V represents the voltage across the conductor, I represents the current through the current conductor, and R is the resistance of the conductor. So, now we are seeing an electron moving with the given energy. We want to see what happens to the IV characteristics, or if there are some impacts on this as we move from one kind of nanoparticles to the other. Second concept which we had discussed in the first week and also in second week was the quantum mechanical formulation of the nanoparticles. Now, in quantum mechanics, the electron momentum along a given direction is quantized. That is the concept which we had seen. Energy is quantized, and therefore, what do you get? You get, let us say, in x direction you will get Px is equal to h cut kx, where h cut is given by h by 2 pi and kx is the component of the electron's wave vector in the x direction. So, we are talking about in one direction. But if you see an electron, it can move in x direction, the y direction and the z direction. Therefore, what will happen? Every conduction electron is associated with a wave vector k, which is given by kx, ky, kz. Now, if you take the set of all possible k values, this will result in a lattice in a reciprocal space. Now, if you take the system to absolute 0, what will happen? The electrons will occupy all the energy states in reciprocal space up to a boundary. So, they will go to the minimum energy state and then they will start occupying the levels, and depending upon of electrons which are there associated with the given element, you know that they will fill certain level of energy levels, and this allowed state in the reciprocal space up to a boundary that is called as Fermi wave vector or Fermi level given by kf. So, this is equivalent to filling a sphere in reciprocal space with a radius of kf if you take all the 3 dimensions. So, you have a system and all around it up to a certain level you have the energy levels which are occupied. So, let us see what is the corresponding Fermi energy. Ef is given by h cut square kf square by 2m. If it is at 0, you will find that up to the Ef level you have all the energy levels are occupied and beyond that they are not occupied. But when you increase the temperature, that means you go from T is equal to 0 to T is equal to T1. So, what you will get? You will find that there would be an additional factor which will come into picture, and that is the thermal energy K beta T1 in this case, and you will find that the energy levels beyond the Fermi levels will also be occupied by certain number of electrons, because they will get excited and go to a higher energy level because of this thermal energy. Hence, what you can clearly see that the electron energy will depend on the dimension of the system, and number of conduction electrons at a given energy will depend on value of energy, the dimensionality of the system, because you are writing in terms of Kf and what is the radius of this sphere and what are the energy levels up to which they are getting filled. So, if you write the Fermi region lengths in 1D, they would be equal to 2 kF. In 2D, it is an area. So, you have pi kF square, and in 3D you have the volume, and that is given by 4 by 3 pi k F cube. So, now you can clearly see as we move from 1D to 2D to 3D confinement, clearly the Fermi energy and the Fermi level changes. Now, let us relate the K space unit cell with electron count, that is the number of electrons which are there. For this, what you are supposed to do? You take the Fermi region and divide it by the K space unit cell, that is the size of the K space unit cell. So, the number of electrons are known to be a function of energy which is available, and once you do that, this will yield the dependence of electron count on energy. And the moment you take the derivative of the number of electrons with respect to energy, that is dN by dE, what did we write in the previous lecture? dN by dE is given as density of states. So, what are the states of energy level which are available for the system to occupy? So, this becomes a critical information which we can derive up to now. Let us do some mathematics. So, we have defined dE equals to dN by dE. Now, the number of electrons, let us say in a small energy range dE, so it would become E2 minus E1, that can be written as dN would then become equal to dE by into dE. So, dN is equal to dE, and which is also a small function of E in this case. This shows, so let us write this information mathematically. So, we have seen dE is equal to dN by dE. So, if you take a small energy range dE given by E2 minus E1, we can write dN is equal to dE, which is in the small energy level dE. Hence, what will happen? dN becomes proportional to the density of states. More states means more electrons at that energy level. If you plot for, so if you take the derivatives and then you write mathematically, you will immediately find that for 1D structures you have dE, which is proportional to 1 by under root E. For 2D confinements, you have dE, which is constant, and for 3D, dE is under root E. Clearly, you can see that the density of states have serious modulations as a function of confinement. Now, what are we saying? We have delocalization in one direction, two directions, or all the three directions. Then we can write the corresponding n. We will take density of states dn by dE, and you will get the corresponding values. If you plot the number of electrons in a certain range, or you say number of electrons in a particle is a function of energy which is available for the system to operate, then it will be n, which is a function of E, as a function of E. These are the parameter curve which you will get. So, 1D, 2D and 3D. Correspondingly, you will get the curves for dE, which is also a function of E. Now, clearly you can see that they are very different. So, dE for a system which has one dimensional structure, then what you will see, dE is initially high, but then it falls down, and for 3D structures, that is 3 dimensional delocalization, it is entirely different. So, you have to choose what type of material would you use for actually making a device if the change in energy is large or small. So, that you can actually get different energy levels which the conduction electrons can occupy, and you can see the variation in the current or the corresponding voltage which gets stabilized along a capacitor, or the current which flows through the conductor. So, now we write the number of electrons and density of states for different dimensions. So, once again we write, you can clearly see that as we move from bulk structure towards dot, you have significant variations in the mathematical formula associated to these parameters. Now, the degeneracies, that is given by di, of the confined energy levels depend on a particular level. Now, if you see the Heaviside step function, this is 0 for x is equal x less than 0 and 1 for x greater than 0. The delta function is 0 for x not equal to 0 and infinite when x is equal to 0, and integrates to a unit area, and the corresponding k1, k2, k3, these are the constants which are there. So, clearly just by looking at these formulas, you can understand that there would be significant change in the properties as we move from different kind of delocalizations. So, let us again look into the graphical representation. So, if you see the NE versus E or DE versus E in quantum dot and compare it with quantum wire, clearly they have very different features. So, quantum dot seemingly has a step like variation, whereas the variation in quantum wire is of different curves coming together at certain points. If you compare now with quantum wire with quantum well, you can see the behaviors are entirely different. Now, here in quantum well, the density of states have a step like function, and if you compare all three of them with the bulk structure, that is the bulk, you can clearly see the function n e d e as a function of E, they are very different from quantum well, wire or dot like structures. So, now it must be very clear to you that as we move from one type of particle to the other, the number of conduction electrons which are available to me is changing significantly, and the variation is quite prominent as we move to higher energies. Now, the density of states also change, and therefore, the corresponding properties are going to change in these systems. So, we had been discussing about effect of shape, size, that is morphology on particles more qualitatively. We were proving it with certain logics, but now we can prove it mathematically and drawing the corresponding mathematical equations graphically, we can also show it at one go that the properties are going to be different. We have seen that as confinement occurs, their energy levels become quantized, and the quantization arises in all types of regular or irregular particle shapes as long as there is confinement which exists. And then we have explained all these phenomena by considering the Fermi gas model, and now the moment we have drawn it graphically, the Ne versus E or dE by E, we can see that the energy levels which would be there or the number of conduction electrons which would become available to us would be very different. That means, the electronic, optic or even thermal properties of these materials would be strongly influenced by their dimensionality or confinement in these particles. Now, if you see, let us say, what is the role of density of states in thermodynamic and magnetic properties of material. We will discuss these things in more detail in subsequent weeks, but just to give you an idea today why these properties would change. Now, if you see the density of states particularly at Fermi level is affected, and it also affects various properties such as specific heat, magnetic susceptibility and thermal conductivity. Thermal conductivity more so indirectly because of the phonons. Now, if you see the specific heat, what is it? Specific heat is of a solid is the amount of heat needed to raise its temperature by 1 degree. Now, at higher temperatures it is predominantly coming in from the lattice vibrations, and the phonon related contribution depends on the phonon density of states. but at lower temperatures an additional component arises from the conduction electrons. This contribution is particularly important in metals and is given by pi square d EF k beta square T by 3. So, this is the formula. If I tell you that why the properties should change, you can clearly see that the properties would change because EF is changing and therefore, all other properties are going to change significantly. Similarly, if you look into magnetic susceptibility, you will find that the Pauli's susceptibility is also given as mu b square d, which is a function of EF, and where mu b is the Bohr magnetron. Now, clearly as d, which is a function of EF, is changing, you are going to see the susceptibility also changing. Therefore, both specific heat at low T and magnetic susceptibility increases with the density of states, which is a function of EF. Sometimes you will find that questions come and you may also actually think as to how do we measure the density of states. There are various methods which can actually be used for measuring density of states. Today I will just list some of them, and in the last 2 weeks of this course, where we will dedicate full time on understanding the characterization tools used to characterize these nanomaterials, we will talk about these techniques more in detail. So, you can use X-ray emission as a probe for calculating or estimating density of states. So, when let us say you take aluminum and bombard it with high energy electrons, they will eject electrons from the inner energy levels. So, what will happen? This would create hole in the inner core level. Now, electron from a higher level or conduction band may fall into this vacant level, and because of this you will have emission of X-rays. Now, the intensity of these emitted X-rays is directly related to the density of states of conduction electrons. The probability of an electron at a specific energy jumping down to fill this vacancy or hole is proportional to this density of states. Therefore, if you plot the X-ray emission intensity versus X-ray energy plot, this will resemble the density of state, which is a function of E, versus E curve. And for aluminum, these emitted X-rays fall in the energy range of 56 to 77 electron volts. You have another technique which is very sensitive towards DOS, that is photoemission spectroscopy, which measures electrons emitted by photon excitation and gives direct information about the occupied states. You have Seebeck effect, and you can measure that, where the number of electrons which have different energies actually contribute to thermal voltage is estimated, and from there you can predict the density of states. Similarly, you can have carrier concentration calculations in semiconductor, or you can measure optical absorptions and dielectric constant measurements. From there you can estimate density of states. You can perform the NMR studies and then you can calculate density of states, or you can have the Haas-von effect measurements where you can again estimate density of states. So, we have various techniques using which these density of states can actually be estimated, and we will talk about these techniques or at least some of them in the final 2 weeks of this course. So, in today's class we have actually managed to talk about the concept of Fermi gas, how density of states governs the key materials properties like heat capacity and magnetism, and how quantum confinement modifies DOS and leads to quantization of energy. In the next class, we will talk about Coulomb interaction, single electron tunneling, and how these phenomena actually allow you to make advanced nanoscale devices. These are some of the references which would be very useful to understand more about these topics, and you should go through these references to develop better understanding about the topics we have discussed today. So, thank you very much for attending today's lecture.